Hi everybody, welcome back to Chem 121. This morning we are going to be finishing up Chapter 5. Just making sure I get the music stopped there. Let's see here. Administrivia for this week. So lab worksheet number 2 closes tonight, so that is the last call. Make sure you get that in before the deadline. You have exam number 1 tomorrow. Remember that if you want your exam date moved to Saturday at this point, I can't move to Thursday because Thursday is already halfway over. I can do that, but you have to email me before midnight tonight. I will not honor any requests on Friday to move the exam off of Friday because that's your exam day. So make sure you get those requests in. If you sent one to me this morning and I haven't gotten back to it, I will do that later today. I just don't ever have a chance to check my email before class starts because I'm coming in from errands and lunch and things like that. So, yeah, so we got to get through the rest of this because the exam is chapters 1 through 5. So that means that this content is on the exam. So let's get over it. All right. In the previous sections, what we have been doing is drawing Lewis structures, and we were drawing them as, you know, flat things on paper, like this, so maybe this was what we would do for CH4. Not exactly how I just drew it there, but that would be the end result, and it would look like this flat, square, or T-shaped thing, or whatever. Now, it turns out that drawing molecules as flat representations is misleading, because in reality, we are three-dimensional, and we are made of molecules. So all matter exists in 3 dimensions. So we need to do our best to try and interpret it as such. And you can see with this picture here of this model that I have some of these hydrogens are coming out of the plane of the board here. So this would be out of the board, whereas this one would be kind of into the backdrop. So what we're going to try and do is we're going to try and visualize that perspective by drawing our Lewis structures in a particular representation. And so we're going to be able to model the geometry of a molecule entirely based off of the Lewis structure that we would draw for it. So drawing a sketch of the Lewis structure, how we've been doing it so far, is good, but we're going to try and improve it based on the information we have from that sketch. And so this idea is called Vesper Theory. And we'll talk about what Vesper Theory means on the next slide. I thought it was on this slide, actually. But the premise behind Vesper Theory is, okay, I have an atom. Here's my atom. And then around that electron, or that atom, I have bonds to other atoms. And then also maybe electron pairs. And if I was going to highlight the regions where I would say, yeah, electrons are in this space, I would say, okay, here, and here, and here, and also there. Where are there electrons? Well, electrons are in all bonds. So bonds are electrons, and so are non-bonding pairs. So what we're going to do is we're going to say, okay, each of these things we're going to call this. We're going to count what are called electron groups. And when I'm counting electron groups, I'm going to count either bonds that exist around the central atom or non-bonding pairs. Now, more specifically, I am counting locations of these things. So what I would do for this molecule is I could say, okay, there's one location of electrons, 2, 3, 4. Now, if I had a different molecule here, say this molecule where I had like C double bond O, and then Cl, and then maybe an electron pair. And I said specifically around the central atom right here, where are my electron locations? Well, here's a bond around the atom. Here are 2 bonds, but they're in the same location, so we'll just count it as 1. And then here's an electron pair. So the number of electron groups that would be around this carbon would be, okay, I've got a bond here, I've got bonds here, but I'm only going to count it as 1 location. And then an electron pair here. So again, I am counting either any number of bonds in a spot, or if there's a non-bonding pair in a spot. So I would say there are 3 spots here. There are 3 electron groups. But for this one, there are 1, 2, 3, 4. So that's going to be our task, first and foremost. When you draw your Lewis structure, how many locations around the central atom contain electrons? Now you'll notice over on my drawing over here, I didn't count these, right? So these are all electron locations. Why didn't I say that there were like 5 extra ones? These are not the central atom. And so we ignore them. So whenever you get a structure, you're going to always consider the location of these electron groups around the central atom. Because the next step is to apply the logic of how do electrons behave. Well, we said that bonds have electrons. Ooh, sorry, hold on. Grabbed the pen in the wrong orientation there. We said that bonds are made of electrons, and we also said that non-bonding pairs are made of electrons. So what will these 2 entities do to each other? Well, electrons will always repel each other. So therefore, any bonds will repel other bonds around a central atom, as will electron pairs. Oops. So when we are drawing our geometry, any electrons that are in electron groups will push each other apart to the maximum distance that they can. Because this is just a fundamental force that happens. Electrons don't want to be crowded up next to each other. There's only room for 2 electrons in each region around an atom. So we're going to try and spread those regions out as much as we can. All right, and so this is called Vesper Theory, or valence shell electron pair repulsion theory. Now, what the heck does that mean? You actually know all these words, believe it or not. So, valence shell means that we are using valence electrons. Electron pair means, well, it means what it says. Electrons occur in pairs, either in a bond, which is 2 electrons, or a non-bonding pair, which is 2 electrons, right? And then repulsion. Electrons repel. And then the word theory just means that we understand this very, 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 very well. We have done lots and lots and lots of experiments to lay the groundwork for this understanding of how matter behaves. So this is, and we shorthand it to Vesper because, I don't know, Vesper never caught on, so we just call it Vesper. All right. Now, so there are our electron groups. Remember that bonds or non-bonding electrons will count as groups of electrons. We're going to count the groups. And then finally, once we have counted the number of groups, which we're going to assign as electron groups here, we're going to assign a shape. Everything with 2 groups will have a certain shape. Everything with 3 groups will have a different shape. Everything with 4 groups will have yet a different shape. All right, let's look at those shapes here. In pink is the central atom. The white atoms on the outsides are going to be whatever atoms that they are in your structure. So they're colored white here, but they aren't necessarily hydrogen. If you're familiar with how models color specific atoms to represent different things. So here, pink is just the central atom, and white is whatever atom you want it to be. If I have 2 electron groups represented by the white spheres here, they will repel each other in space as much as they can. And so they will get the maximum angle away from each other, which forms a 180-degree arrangement. Well, the angle for a line is 180 degrees, so we call this linear. For 3 objects, we sort of just push away from all of our neighbors to the furthest that we can without causing any one of these angles to be smaller than the others. And the result that we get is that each of these is 120. So what we have created when we do this is a sort of triangular arrangement that we call this Trigonal Planar. Now, the final arrangement for 4 objects around a central atom looks a little bit different than what we're used to, right? Normally, we would have guessed something like this, so we'd have up, down, left, and right, yeah? But it turns out that these angles are only 90 degrees if I do that. If I use a third dimension, you can see that this is slightly more than 90 degrees. In fact, it's this. All these angles are 109.5. And the reason that I can do that and have more than 100 or more than 360 degrees going around this seemingly is that I'm not actually going in a complete circle. I'm using 3 dimensions. So that forces our molecule to adopt this shape. A sort of 3-dimensional little pyramid, which if I draw, I'm going to get rid of the lines on the screen here. If I go like this, and I just draw on the edges of this really thickly, and then I go like that, you could see my pyramid, and then this would be the back line behind it. Now, the pink atom in this case is actually trapped in the center of the pyramid. But you can see that this is creating a 3-dimensional shape, and it's called a tetrahedron. A tetrahedron is a regular solid, i.e. a sort of 3-dimensional shape, that has 4 faces, all of which are the same. They're all triangles. If you've played Dungeons & Dragons, this is your D4. Alright, that's the first of our 3-dimensional shapes, and in fact is the only one we're really going to talk about in this class for these 3 basic shapes. So n can actually go up to 5, 6, 7, 8, 9. 6 is common, 5 is common, past 6 is not super common. But for our purposes, we're only going to do n equals 2, 3, and 4, because we're only... Yeah, they're caltrops, there you go. We're only going to consider molecules that obey the octet rule in this class. Now, because I've mentioned that, that does imply the existence of molecules that do not follow the octet rule. Yes, there are plenty of them, but that's beyond the scope of Chem 121. So we're not going to worry about those. We're going to just deal with things that conform to the octet rule, and we'll only have 2, 3, or 4 electron groups around the central atom. All right. These are going to be our families for shapes. The word that your textbook uses is called Vesper Geometry. So again, you're going to draw a molecule and assign it a Vesper geometry. So let's do an example here. Oh, that's not convenient at all. There we go. So let's do this here. So I'm going to draw a molecule here. And I'm going to just draw its Lewis structure. Like this. And what I would want you to do is I would want you to say, what is the Vesper geometry of this molecule? And so what you would do is you would say, okay, I'm going to count the electron groups around the central atom. The central atom is silicon. How many electron groups are coming out of it? Well, here's an electron group, because I have bonds in that space. And here's an electron group. So there would be 1, 2 electron groups. And then just as a reminder, remember, any number of bonds in one location equals 1 electron group. So even though there's 2 bonds there, it's only 1 electron group, because they're in the same space. And what we're caring about here is spatial arrangement around the central atom. If the bonds are in the same spot, they're going to count as 1 electron group. How many electron groups did we get? 2. Therefore, the geometry of this molecule is linear. Let's do another one. Let's suppose that I had ammonia, which looks like this. This is how we've been drawing it lately, right? How many electron groups are around the central atom of ammonia? So I'd go 1, 2, 3, because I got 3 bonds coming out. And then I have this electron pair. So that would be 4 electron groups. So what would the Vesper geometry be? Well, it would be tetrahedral. And there you go. So if I really wanted to draw ammonia, what I would do is I would put the nitrogen in the middle. That would be the pink atom. And then I would have something going out to the side here. Something coming to the front. Something sort of going to the back here. And then in the other position, I do that. And so that should look like my molecule right up here in this diagram. In fact, if I really wanted to, what I could do is I could just go over here and I could say, okay, well, here's my nitrogen. Here's my hydrogen, 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 electron pair. And it'd look like that. That's what ammonia looks like. So again, every molecule that you draw in this class should conform to one of these shapes. And you can just append the atoms directly over these little diagrams that we have here. And you should be able to do that. That will tell you what its Vesper geometry is. I accidentally flipped that forward before I meant to do this. So let's go back here real quick, just so you can see it. All right. So the family is going to be the Vesper geometry. Now, if that was it, we would call it a day and we'd be happy. But now what we're going to do is the next step is we're going to assign both the Vesper geometry, which we already did, and something called a molecular geometry. And the molecular geometry is the shape that you observe if you understand that electrons are basically so small that you can't see them. So what I'm going to do to illustrate that is I'm going to go back over here. You could see my NH3 molecule like this. But if I take the highlighter And I don't know if this will work. It totally won't work if I do it that way. That must just be an eraser. We're going to do it this way. I'm going to go like this. I'm going to just do this because my electrons aren't actually there. They're too tiny to actually see, right? So instead, the shape that I observe is something like... Now it's just this. It's this tiny squished pyramid, right? As opposed to where it used to be, which was up here. So we have changed the shape of the molecule by excluding the orientation of the electrons from the overall shape. So that's going to lead us to a molecular geometry where we get a different result. And so what I'm going to do here is first I got to click on this. And then I'm going to paste this link in the chat because this is super helpful to you. And you can play along with this at home if you'd like. And let me bring up on the screen what this looks like. Well, unfortunately, that's a little too small. There we go. All right. This is the molecular shape generator. We're going to use the model for now, but you can look at real molecules in a second. In fact, we will here. So what this is doing is it is modeling a generic molecule with a central atom and some number of electron groups around it. We've represented them as these just atoms that are bonded using however many bonds. Now, you can put single bonds in here, and you can see how the molecule's geometry changes. And then you can spin it around and observe that. Now, you'll notice also that whether I put one bond or two, so there's one bond, but if I put two bonds in, I get the same effect, right? Now, this obviously breaks the octet rule, but it's just a model. Like, I could even do this if I wanted to. Look at all the bonds you get. And the geometry is still the same, so we still get a tetrahedron. All that matters is that we have a location with bonds around it. So one location, two locations, 3, 4. That will tell us the number of electron groups, and thus the Vesper geometry, which unfortunately in this is called electron geometry down here. So as I add and remove these things, these names should be familiar, and of course they are. Now, here's a question. What if I add electron pairs here instead? Well, the same thing happens, right? I still have a tetrahedral geometry. It's just that my electron pairs here take up the space of the bond instead. And those are still arranged in a tetrahedral arrangement, if you can see it. So I've got something going up, something going sideways, and then going forward and then backward, right? You can see that here. Now, in reality, electrons are very, 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 very small. It's very hard to see electrons. So if I click on this, boop, now my electrons are invisible. I can't see electrons because they're really tiny, right? But the force of their charge still exerts itself on all the other electron groups. So this is what you would actually see in reality. You would see a molecule that looks like this, which looks a lot like water, doesn't it? You've probably seen water drawn with the bent angle. It turns out that's why we draw it this way, is because there are lone pairs on water. All right. So what we need to do is we need to assign names to different molecules here. So if I add all bonds around my central atom, the molecular geometry is going to be the same as the Vesper geometry. It's only when I add electron pairs that they start to change. You're going to notice that there are a lot of differences in names between these two. There's all sorts of different possibilities here. And fortunately, we're only going to consider 4 things. But if we had 5 or 6, you'd get a bunch of them. So what we're going to do now is I'm going to go down here to the real molecules thing. And here's a bunch of different molecules. We're not going to use most of these because, like, for example, this breaks the octet rule. So we're not going to consider that. But we'll look at water. We'll look at CO2. Here's SO2. That breaks the octet rule, actually. BF3. I don't know which of these are actually safe to show for this class because a lot of them have 5 or 6 electron groups, which exist, but again, beyond the scope of this class. So what we're going to do is we're going to generate all of these shapes, and I'm going to do that by doing this. So we're going to put this here. I'm going to try and make this a little bit bigger. We're going to just stick him down here in the corner. And I need to make this a little bigger, apparently. Okay. All right. So I'm going to just have this hanging out here for now. Actually, hold on. It wasn't very centered, so I was like immediately suspicious. Okay. Ah, there we go. Okay. And then I just realized that as soon as I do this, that's going to go away anyway. So I got to capture it again. All right, we're just going to have that hanging out in the corner here. And then I need this to be on the screen. Somewhere. There we go. So what we're going to do is we're going to make a giant table. And so that table is going to say number of electron groups and the Vesper geometry. And then what we're going to do, we're going to have... I could do better than that. That's worse. My goodness. How about if I just stare directly at what I'm drawing? That was a little better. Okay. And then we're going to have number of non-bonding electron pairs. Molecular geometry. And you can't see half of these, I just realized. There we go. All right, so let's start at the beginning here. So if I have 2 electron groups, then I will have a structure that looks like what you see on the board here. And the geometry of it will be linear. And it turns out that whether I have both of these are bonds or electron pairs, it still forms a line, right? Everything is in a line. In fact, I'm going to put this on the screen to show the bond angle. So that should be present now too. So no matter whether that you have 0 or 1 non-bonding pairs around it, the result that you get is still going to be linear. All right, let's put a third thing in here. And you can see that all the angles around this are 120 degrees. And like we said before, anything with 3 electron groups is trigonal planar. Now, if I have 0 non-bonding pairs, then this is the shape that I get, what you see in the corner there. But if I have one of them as an electron pair, I get this. And remember, electron pairs are so small that we don't see them. Our shape looks like this. It's now just, it's not linear anymore, Even though there's only two visible things, the influence of the electron pair is still felt, but we can't see it. We get this sort of bent line, and so we call it that. Bent. And then if you were to take one of these away and put a second electron pair in there, you'd get linear again because it looked like this. It also looked very inappropriate. So we're going to just get rid of that. All right. The last one that we'll consider, for 4 electron groups, we called that tetrahedral. And if none of them are electron pairs, non-bonding, then the molecular geometry would be the same, right? But let's get rid of one and replace it with an electron pair. And you'll see that it looks a little bit different once I remove all the lone pairs there. So it's no longer as tall, right? There's no longer this tall part. So if I have one electron pair present in my tetrahedral Vesper geometry, the new shape that's going to be called is Trigonal Pyramidal. Because it looks like a tiny pyramid. And the base is a triangle. And you can see that this purple atom is not level with the rest of my atoms here. It's hard to spin this. But there, now they're all in the same plane in space. And this purple guy, a little above it. Alright, what if I did this? I put a second electron pair in there. You'll notice that now, when I hide these, it looks an awful lot like the bent line that I had before, right? And so that's actually what it's called. Now, the difference between this bent and the previous bent is simply the angle that's in there. You don't need to know the angles. You just need to know to call it bent. But there are basic shapes here for both Vesper and molecular geometry. So what you're going to do is that you're going to draw the Lewis structure of any molecule. For example, if I drew, say, let's draw this again. And what you would do is you would say, okay, I'm going to count the electron groups. So I got 1, 2, 3, 4. 4 electron groups. So what is its Vesper geometry? Okay, which of the groups, 2, 3, or 4, does it belong to? Excuse me. It's this one, right? There are 4 electron groups. So its Vesper geometry will be tetrahedral. Of those 4 electron groups, 1 was an electron pair. What will its molecular geometry be? And so in the 4 group up here, we would say, okay, 4 electron groups, one of which is an electron pair. So its molecular geometry would be Trigonal Pyramidal. So that's how we're going to assign geometry. Draw the Lewis structure, step 1. Figure out what its Vesper geometry is, step 2. So it's going to be either 2, 3, or 4. Let me move this up out of the way here. And then once you've determined which Vesper it is, step 3, figure out which member of that family it is. So these are going to be families on the left. These are going to be individual members on the right. Let me just draw a little separator here. So we'll separate out 3 from 4. And I cannot click on this for some reason. Oh, I really screwed it up, didn't I? What have I done? And we'll separate 2 from 3. There you go. All right. So let me erase this down here so that I don't have... There we go. So there's our table, and then I'll just Control-Shift-N so that now I can draw all over it for examples here. Woo! Look what I can do, and then just go, boop, we can just erase. So we're going to use this table to do all of our examples. So let's go do the examples now. All right. So, oh, we already did NH3. So let's do CO2. What I want you to do is I want you to draw the Lewis structure for CO2. Tell me what its Vesper geometry is, and then tell me what its molecular geometry is, and then I'm going to build it over here in this model viewer in the corner. Okay, so type that answer in the chat, and I'll check in with you in about 2 or 3 minutes. All right, one more answer, or 1 more minute, we'll go over the answers. All right, so first, let's draw the Lewis structure. I'm going to try and draw that on this page. Well, actually, no, I'm not. I'm going to go over here. Because I need this chart, duh. All right. Oops. Hold on. Let me get rid of all this here, too. Boop. All right, so let's draw CO2. You know, with the pen tool. And you should have drawn this as your Lewis structure. And then we would say, okay, if this is my central atom, how many electron groups are around it? 1, 2. So 2 electron groups means that its Vesper geometry is what? And we go up here, and you see, oh, well, two electron groups is always linear, right? Of those 2 electron groups that I circled, how many are non-bonding electron pairs? 0 are non-bonding electron pairs. So the molecular geometry is also linear. And like we said up here, it doesn't really matter what you get. The answer will always be linear if the if the Vesper geometry is also linear. So that would be what I would fill in. Okay, let's go build CO2 over here. Well, I've got 2 double bonds. Boop, boop. There we go. Uh-oh. Sorry, hold on. There, there were hidden alone pairs, and I was like, wait, what? Why did that happen? I thought I had cleared everything, and I had not. So there's our molecule for CO2. Oops, I didn't actually do that. There we go. All right. I'm going to give you 4 more problems to try. So tell me the Vesper geometry of each of these, and then tell me the molecular geometry of each of them. Start by drawing a Lewis structure. If you have a choice of how to draw your Lewis structure, try and make it as symmetrical as you can. We'll go over the answers in about 5 minutes, and then we'll take a break. So see you in a bit. One more minute, we'll go over the answers. All right. So we've got ozone here. Let's go back over to this screen here. Oops. We'll just put these over here for now. So we'll clear the board. And so we got ozone. So ozone, I'm not going to go over how to draw the Lewis structures at this point because we should know how to do that. But your Lewis structure should look something like this. I just have these memorized at this point. So 8, 16, 18. Okay, so there's ozone. We're going to look at the central atom. I'm going to say how many electron groups. So 1, 2, 3. So I'd say 3 electron groups. So the Vesper geometry is trigonal planar. And then of those 3 electron groups, I indicated how many are electron pairs. Well, one of them is. So the molecular geometry would be, so if I was trigonal planar and I have 1 electron pair, it would be bent. So this should be a bent line, and if I draw it this way, so if I go doot, 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 there you go, and then I hide this, that's what ozone looks like. And that's still in the corner, right? Yeah, okay. All right, so there's the first one. So I will hit clear on that, and we'll do the next one. We've got SnCl3. Wait a second, I thought tin was a metal. Sorry, I'm drawing my structure here before I answer that. Tin is actually close enough to the nonmetals that we can use it in this way. And then it's negative, so I got to put this minus charge on it. There we go. All right, around the central atom, which is this one, how many electron groups are there? So 1, 2, 3, 4. So 4 electron groups, the Vesper geometry would be tetrahedral. And of those 4, 1 is a non-bonding electron pair. So that would make it trigonal pyramidal. And if we go over to our little structure here, and I hit reset, So I have bond, 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 electron pair. It'll look like that. And if I get rid of the lone pairs, it'll look like that still. All right. And then we'll clear. We got SeCl2. That looks like this. How many electron groups are around it? So 1, 2, 3, 4. 4 electron groups. So the Vesper geometry is tetrahedral. So why are there 2 dots on the SN? Wouldn't there be one left since it's group 4? So remember that we count valence electrons for our molecules by adding all the things together. But then there was this minus charge on there. And this minus charge right here, let me get the pen out real quick. This right here is an extra electron. Because how do you make it negative, right? So if I had like O3, that'd be 6 times 3, which is 18 electrons. But if I had O3 with a 2 minus, I would add an extra 2 because that makes it 2 minus. 2 extra electrons would give it a 2 minus charge. So there must be 2 more electrons there. For 1 minus, there must be 1 additional electron there. Where am I on my slide? There we go. Okay. So I got 4 electron groups, but around this, I have 2 of them are electron pairs. So 2 non-bonding electron pairs. So the molecular, I guess, I don't know. I'm flipping words around. So the molecular geometry of this would be bent. And so how do we get that shape in here? So if I take one of these away and if I put this in there, there's our bent. All right. How did we get the negative charge in there? So the negative charge is in the formula just so that that's what we observe. So for that molecule SnCl3, there is a negative charge on it because an extra electron is required. So with the formulas, it's not going to be possible to predict what their charges are all the time, so I will tell you what they are. So if you see something that has, like, on its formula, something like this. Oops. So this means 2 extra electrons. So this would be 4. This is 3 times 6. And then this is an extra 2. So 18, 22, 24. So that's how you get that. You have the negative charge because that's how many electrons are present for you to do bonding with. So, like, I gave you this molecule, and it just happened to have a negative charge on it. You include that in your bonding. It's not because of the octet. The octet is the result of how do I arrange all these electrons. Oh, I'm doing carbonate next anyway, so we'll just draw the Lewis structure here. So there's my carbonate. And yeah, this is just part of the structure of carbonate. If I did not include the 2 minus, I would have a totally different structure because I'd have 2 fewer electrons and my shape would completely change. So whenever you see a charge on an ion, it just comes with the ion. It's just part of it. There's not really anything special about, like, well, why is it there? It just kind of is there. It's part of the structure. All right, so for carbonate here, if I count electron groups, I got to change my ink color here. 1, 2, 3 groups. 3 electron groups. So the Vesper geometry will be trigonal planar. Because that's what 3 groups is. And of those 3 groups, 0 of them were electron pairs. So no non-bonding electron pairs on the central atom. So the molecular geometry is also trigonal planar. And we can draw that over here. So let me, oops, there we go. Oh, no, there. All right, that's what I want. There's the structure that we drew. All right, that's molecular geometry. So your job, again, is to assign a Vesper geometry and a molecular geometry to any structure that you draw, and you'll be asked to do that on the test tomorrow. Oops, sorry, my little diagram is covering up the chat there. All right, we're going to take a break because I sailed right past the break time. So we're going to take 10 minutes, and when we come back, more of this. Ha ha ha, that's adorable. That's actually the little picture from the music that I'm playing here. Oh, I hit mute before I wound that down. So, yeah, just in case you were curious, I just get all your music for the breaks off of YouTube. So, yeah, I did not actually put the homework practice on the screen here for the section. So that is right here. Oops, I cannot select this for some reason. There we go. So there's the homework practice for this section. Remember that your objective for this is to be proficient in determining the geometry of a shape, and then determining its both its Vesper geometry and molecular geometry. All right, in the next section, what we're going to do is we're going to apply the idea of geometry to a new concept called electronegativity to finally determine whether something is polar or not. You may have heard of the term polar. Something is polar if it dissolves in water, and if it's nonpolar, it doesn't. It forms a separate layer, or things like that. In Chapter 7, we're going to talk about that in more detail, but in this chapter specifically, we're just going to identify, is it polar or nonpolar? So, that's our goal here. Now, we know that in a covalent bond, we share electrons. And we also know that in an ionic bond, electrons are transferred from one atom to the other to form our ions. Now, these seem like very binary states, but it turns out that you can actually share electrons unequally. For example, maybe one atom gets the electrons more of the time. They just end up closer. An example of this would be if you have 3 children that all have like access to one, I wanted to say Game Boy, but that doesn't exist anymore. One Nintendo Switch. And so they share the Nintendo Switch, but one of the kids keeps it in their room. So is it shared equally? Well, no, of course not, because it's in one person's room over the other 2 children's, right? So in this case, the Nintendo Switch would be your electrons, and the 3 kids would be the 3 atoms that are involved in this transaction, right? So with atoms, it's the same thing. Your electrons can be shared unequally. And let's look at some examples of that. Here's an example where you'd be sharing electrons exactly equally. If I had 2 chlorine atoms, and the chlorine atoms were trying to pull the electrons closer to themselves, which one would win? Nintendo's remaking the Game Boy. Of course Nintendo's remaking the Game Boy. Nintendo has no more good ideas, right? Let's just reuse all the old ideas. I don't even know what happened to my Game Boy. Goodness, that's so old. Nintendo, why? Anyway. If I had these 2 chlorines like this, and they were pulling electron density towards themselves through this bond, they would pull equally. And where I would say that the electrons end up is exactly in the middle of the bond. So the electron density would be exactly in the center. They would not be pulled more or less towards one side. But what about this molecule? Now, hydrogen's really small. There's only 1 proton in it, whereas chlorine has 17 protons in its nucleus. Chlorine wants the electrons much more. It's a nonmetal, right? So the electrons are going to go in this direction more than they're going to go in this direction. And so I would say that the density of the electrons would be closer to this end. Now, is it completely on that end? No, if chlorine just took the electrons for itself, you'd have an ionic compound. But HCl has a covalent bond. You can think of it as like a ionic bond. Oh, excuse me, bad time for a yawn. You can think of it as an ionic bond, but it's not quite there yet. It's definitely on the way to becoming one, though, in terms of where the electrons spend most of their time. They spend it near the Cl. So we would say the electrons are, in general, closer to chlorine than hydrogen. And what that means is that the molecule doesn't have an equal distribution of electrons. We would say that it is polar, because more of the electrons are on this side than there are on this side. Now, later on, we're going to learn that we can draw symbols for this. So I draw something like this, or I would draw something like this to represent that my molecule is polar. But first, let's talk about this concept, electronegativity. Electronegativity is a ranking of atoms of how strongly they will pull electrons towards themselves. Now, this is going to be electrons that are in bonds. You can't pull electrons through space because we have to have some sort of way for the electrons to get over there. So, any bonds that are attached to an atom, the atom's electronegativity, which is an intrinsic statistic or value, will dictate how strongly the atom will pull the electrons towards its nucleus. We're going to rate electronegativity on a scale of 0 to 4. 4 is the highest and 0 is the lowest, and the chart looks like this. Now, if you go to P-table, I believe they also have electronegativity. So let's see here. Oops, P-table. I have a chart here just shown on the screen. Yeah, we have one of these on P-table. So if you want to look at your own copy of this, I have linked the electronegativity table on P-table. Fluorine is the most electronegative element. If you are paired with fluorine in a bond, fluorine wins and takes your electrons. End of story. Nothing pulls electrons towards itself stronger than fluorine. Any other atom... excuse me. Any other atom, you would just compare the two electronegativities between, and whichever one is bigger pulls the electrons towards themselves. Fluorine just always wins, francium always loses. Now, the general trend is that electronegativity going from left to right across the periodic table increases, and then it also increases as you go from bottom to top. So the top right corner is the most electronegative. The bottom left corner is the least electronegative. Now, there is an interesting thing in the middle here. These elements in the center of the periodic table, those numbers are particularly low. I believe that the numbers that are shown are called Pauling electronegativity. The electronegativity on P-table that I linked to you uses a much more up-to-date system of numbering. And the elements in the middle that I've circled there are particularly electronegative to the point where they resist corrosion very effectively. For example, gold is notoriously hard to corrode or dissolve because it is very electronegative. It resists oxidation by things like, say, oxygen, sulfur, etc. All right. Now, this supports what we discussed in Chapter 4. Elements that are on the far left side of the periodic table, the metals, tend to want to give away their electrons, so they have low electronegativity. All the nonmetals wanted to accept electrons. They have high electronegativity. And then we can conform to the octet rule that way, right? Metals want to ditch their electrons to attain an octet. Nonmetals want to accept electrons to get closer to an octet and eventually get there. So we're going to use this idea to determine polar, nonpolar, or sort of in the middle. Or actually ionic, I guess we'll say, which is not in the middle, which is beyond polar. Polar is the one in the middle. I apologize, I mixed that up. So you're going to look at the difference in electronegativity for your elements. And if it's, I'm not going to say less than 0.4, I'm going to say 0.4 or less. And there's a reason for this. We're going to call that nonpolar. So, for instance, let's look at the CH bond. So, C has an electronegativity of 2.5. H is 2.1. I'm using this table, by the way, these numbers, because I've memorized them. The difference would be 0.4, which we would say nonpolar, because it is 0.4 or less. So CH bonds are nonpolar. If the difference between our electronegativity is between 0.5 or 2, so 0.4 we're going to call nonpolar, so we're just going to leave that there. I'm going to change this to 0.5. Then we're going to call this polar covalent. That means that the electrons are shifted towards the side of the molecule that has the higher electronegativity. Or the side of the bond, I should say. If the molecule is just two atoms bonded together. Now, if we have a metal involved, your textbook wants to call this ionic. This is sort of a generalization, but we're going to use it for this class. If you have a metal involved in your bond, treat it as ionic. That will be good enough for our purposes. Finally, if you get an electronegativity that is greater than 2, the difference between your two atoms is greater than 2, that is, we're going to call it ionic. All right, let's do some examples here. I have HF. If I look at the electronegativities of HF, well, F is 4.0, and hydrogen is 2.1, according to the chart that's in my slides. Yes, I realize the P table I sent you is a little different. But the difference here is 4 minus 2.1, which is 1.9. So we would say that this is polar covalent. If it's polar, I cannot do this. These would be for something that was ionic, right? Because it makes ions. So, it's not ionic. We just said that. It's polar covalent. So I cannot put whole charges on my molecule. Instead, what I have to do is I have to use partial charges. And that's what these symbols are. The little delta symbol here represents a partial positive charge and a partial negative charge. We put the partial molecule, or the partial marker, I should say, on the correct side based on electronegativity. What is polar covalent? Polar covalent means that it's still a covalent bond, but the bond is polar. And you're going to find your electronegativity on the chart that I showed on this slide, right here. So these numbers. Or you go to P table, you click that link that I linked, and it will show you all the electronegativities of all the atoms. that you can just scroll through and look at. So this is a way of labeling electronegativity. We're going to put delta positive on the positive side of the bond, delta minus on the negative side of the bond. The higher the electronegativity, the more negative it is. The lower the electronegativity, the more positive it is. The other application that we can use is we can draw an arrow, and the arrow is going to be drawn pointing towards the negative end of the bond. The little dash across the arrow is the positive part of the bond. It almost looks like a positive. That's why we do it that way. Now, depending on the application, you're going to want to use either the delta method or the arrow method. In a second, we're going to be using the arrow method to determine whether an entire molecule is polar versus just a bond. Here, we're just looking at one bond at a time. But in a second, we're going to consider all the different bonds in a molecule. And so what we're going to do is we're going to use these arrows, and we're going to try and plot them all next to each other on our paper. And then we're going to do something that I call follow the arrows. They show you where the electrons go. And what we're going to do is we're going to shuffle our electrons along all the polarity arrows. And if the electrons have moved across the molecule in that manner, the molecule must itself be polar. But if all the arrows result in the electrons just traveling back to where they started, then we end up with nonpolar. So this is going to look easier in practice than what it actually is when you're drawing this. We're going to do the best that we can. So let's look at an example here. So here's CO2. I have drawn its Lewis structure. I have drawn it with the correct geometry. So the molecular geometry of CO2 is linear. So I've drawn this in a straight line. And then what I have looked at is that the delta electronegativity is for oxygen is 3.5. And then for carbon it's 2.5. The difference is 1.0. So this is polar covalent. And I would draw my arrows pointing in the direction of the more electronegative atom. I didn't put this one on the bond. I really should have. I'm going to hit clear in a second anyway, but that's okay. All right. What that gives us is these two arrows. Zoop, zoop. My electrons are going to travel along those arrows, but they're going to do it in a stepwise manner. So what I'm going to do is I'm going to slide these arrows over here, and I'm going to attempt to sum them together. The way that arrows add in this case, or vectors, I should say, if you've done any sort of physics class before, you put an arrow down, and then you start the second arrow where the first arrow ended. So that would look something like this. So here's my first arrow. So I started here. So I'm going to take the start of my second arrow, and I'm going to start it right there. And so that's going to look like this. All right. Where did the electrons go overall? Well, they started here, and then they went over here for the first arrow, and then they went back here for the second arrow. So my starting point and my ending point are the same. In other words, my electrons did not move overall. There is no net polarity. The molecule is nonpolar. So to look at our molecule, we do it this way. My electrons got pulled this way, but the other bond pulled them right back. So they just stayed right in the middle where they were supposed to. If the electrons don't get pulled in one direction through a bond, the molecule isn't polar, right? It'd be totally nonpolar. All right, let's look at some more examples here. So here's SO3, and here's H2O. So you'll notice that I've drawn all the arrows along the bonds, pointing at the more electronegative atom. So sulfur is less electronegative than oxygen. So all these bonds point outward. I'm going to just sum them together in some order. So here's my first bond. I started down here. So here's the start. And my bonds directed me to say, okay, I pulled my electron density up. This one pulled it down to the right. This one pulled it down and to the left. Oh, look, I ended up back where I started. So this molecule must be nonpolar. But what about water? Let's do this. So here's where I started. And one of my bonds pulled the electron density up and to the right, and the other pulled it up and to the left. Oh. I did not end where I started. That means in my water molecule, my electrons are moving in this sort of direction. Like this, right? They're getting shuffled towards O. Nothing is pulling them back away from O. So we would say, okay, most of our electrons live on that end of the molecule, and thus the molecule must be polar. So to summarize what we have done, step 1, you got to draw a Lewis structure. Step 2, you got to do the correct molecular geometry. And then step 3, we have to determine polarity using differences in electronegativity numbers, which you get off of the chart in the slides. Or off of p-table. You'll get the same results either way. You'll just have different numbers depending on what you use. All right. Now, it's very easy to draw a Lewis structure poorly, and you get the wrong answer. So be very, very careful that you are trying to draw your molecule as close to the correct molecular geometry as you can. So use the correct molecular geometry, which is why we did all of those exercises in the previous slide. So what I want you to do is I want you to draw ammonia on your paper. And I'll give you a hint. So instead of calculating the electronegativity here, nitrogen is 3.0 and hydrogen is 2.1. Sorry, this is supposed to be an arrow, but it doesn't look like it. So now you know which way to draw your arrows. And you can tell me polar or nonpolar. And then I'll draw a picture of that in about 2 minutes. So give this a shot. We'll go over the answer shortly. All right, let's draw the answer. I see people saying polar in the chat, and that's correct. So if I draw my NH3 as close as I can to the correct molecular geometry, I would get a trigonal pyramidal molecular geometry. And then what I would conclude is that, well, nitrogen is more electronegative than hydrogen. So all of these are going to point in this direction. And nothing is pointing down. So overall, I would end up doing something like this. So if this is number 1, this is number 2, and this is number 3. And you can do these in any order. I would end up doing something like this, right? 1, 2, 3. Or just this. So ammonia is polar. And the electron density points towards the end with the nitrogen on it, because it would be like this, right? All right. So I want you to draw these molecules. Let me put the homework practice on the screen here. I'm going to give you 5 minutes to do this. Actually, now I'm looking at the clock, so I'm going to have to I'm just going to have to give you the answers here. So this is polar, nonpolar. This one's nonpolar. And then polar. Why are they all at the bottom? I'm not sure what you mean. Why I put all my H's here? So I'm drawing it to conform to the geometry of trigonal pyramidal. Remember that our geometry looks like, here's the shape for it. Oh, here's my NH3. It's like this. So I've just drawn them on the bottom side. You could spin this around. You could rotate it if you want to. Where am I? I'm over here. So if you drew it in a different orientation, that's okay. Your arrows would then point in a different direction, but the end result would still be, oh, it's polar. All right, so I do have to give you the answers for these because we do have one more topic that is on the exam tomorrow, so I do have to get through naming. So let's talk about that real quick. Fortunately, naming covalent compounds is not super difficult. I'm gonna just take. You don't need to worry about these rules down here. So these down here, don't worry about this. This is not important for you. But when we write a molecular compound, or a covalent compound as we're going to call it, we're going to arrange the atoms by putting the one that is the most metallic, quote unquote, first. So for example, if you look at carbon and oxygen in like CO2 or CO or whatever, the C comes first. Which element is the most metallic? The one that is the most metallic is going to be the one, generally speaking, with the lowest electronegativity. So if you're looking at a formula and you're like, what element do I type first? Type the one with the lowest electronegativity and you'll be safe. All right. Now, there is a rubric for how to name covalent compounds. And that is the following. So I got to clear out this real quick. Unfortunately, my slides don't include it for some stupid reason, so I'm going to have to go back and edit them. All right, and so here is our naming scheme for covalent compounds. Now, you might look at those rules and think, wow, that's really similar. And then I'm going to just put the little... Oops, not prefix. Prefix. There you go. So Unlike naming ionic compounds, we are going to use numeric prefixes to indicate how many of an element are present. So the prefixes are things like this. So 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta. We got hexa, hepta, octa, nona, and then deca. All right. So we're going to name things just by dropping the number prefix into the appropriate box as we see these numbers. And then you just name the first element, name the second element with IDE. So no Roman numerals for covalent compounds. You use number prefixes instead. Now, we're going to have some little exceptions that crop up here and there when we are dealing with these names. For example, mono is only on the second name, but all the other prefixes apply to whichever one that we have. So for instance, if I had this, CO, I would say, okay, name the first element, carbon. Name the second element with ide. That would be oxide. And then we apply the prefixes. We only use mono on the second element, so we would do something like this. Monoxide. Notice that the O is already included there. If you ever get this, we're going to drop the first vowel. So instead of saying pentaoxide, we would say pentoxide. And those are the exceptions. You will see those as you get used to them. But we do have to be careful. And I apologize, I wish we had more time to spend on this, but I do want to at least talk about it so that you can watch the video a few more times while doing the practice problems. All right. So what would I call this? So I've got nitrogen, and I've got two of them, so I apply the numeric prefix di for dinitrogen. This is oxygen, which as the second element we'll write as oxide, and then this 5 is penta, and I ignore the AO here, so dinitrogen pentoxide. This is all one word. All right, how about this one? What would I call CO2? Type your answer in the chat once you got it. I mean, we all know what this is, right? This is what causes global warming. Yeah, it's carbon dioxide. Very good. So does that conform to our name? So we'd write carbon for C and then dioxide for O2. And again, we don't say mono on the first element. All right, what do I call this? Can't just say water. Water does not follow the naming rules. Dihydrogen monoxide. Very good. All right. That's the naming rules for covalent compounds. You just apply this scheme to any compound that is covalent. Now, on the next slide, I have the petition to ban dihydrogen monoxide. This is an actual thing. That if you look at all of these these things here, that these are all terrible, terrible sounding things, but they're all stuff that water does. Like, if you breathe with water, yeah, you will die. I wish I had more time to go over it, but we really don't. So, let me get the examples on the screen here and the homework practice. Go ahead and try and name as many of these as you can. In the last few minutes, I will write in the answers so that you have them. So, I'll give you 3 minutes. I'll write in the answers in just a bit, and then we'll call it a day. All right, let me just quickly write in the answers here. So we've got dinitrogen monoxide. We've got dichlorine trioxide. We've got sulfur hexafluoride. And then tetraphosphorus decoxide. And then down here, diboron would be B2. Trioxide would be O3. Carbon disulfide would be CS2. And then oxygen difluoride would be OF2. And there you go. So, thankfully, covalent naming is a little bit easier than ionic naming. The real trick is going to be keeping these separate. All right. That is the end of Chapter 5. Hooray. We've covered all the material before the exam. Like, just barely. But we got there, so hooray. I hit a button and it cut out the music. Oh well. There it is. All right. So, just some brief comments about the exam. So, your exam will open tomorrow unless you have emailed me and want to take the exam on Saturday. You need to specifically email me so that I can set that up for you in Canvas, okay? So if you need an extra day to study or you have like a conflict of time or whatever, and you need to take the exam on Saturday, send me an email and I'm happy to move that, but I need to know by tonight. If you email me after 11:59, i.e., you email me on Friday, then I will tell you, please take the exam today, okay? And if you don't, that's obviously very bad, okay? So the deadline to request this is tonight. Please make sure that you ask if you need it. It's there for you. There's no penalty. It's all free, and it's there to help you. That's it. Also, lab worksheet number 2 is due tonight. Best of luck on the exam. Make sure that you ask me any questions today. I cannot help you during the exam time. And good luck. We're all counting on you. Take care.